Good morning, good afternoon, good night, wherever you are. Welcome to this week's edition of HoloTube. We are very happy to have Koenraad Schalm today from the Lawrence Institute in Leiden. And well, you're going to tell us everything we wanted to know about linear resistivity and a lot more. I'm looking forward to it very much, so please take it away.
Okay, thank you very much, Martin. Thank you very much, everybody, for being here. It's indeed, the title is a mouthful: T-linear resistivity, optical conductivity, and Planckian transport for holographic local quantum critical metal in a periodic potential. But as I go along, I will explain you all the aspects of this. And as all of this is in this large paper with many authors, some of them fantastic master students. And there's some background information into two smaller articles. But this is, of course, all part of the story of applied string theory, where we try to explain strange metals and high TC superconductors with virtual black holes. And as almost all of you know, the real mystery of high TC superconductivity is the strange metal phase, which is the phase that appears at optimal doping, not below the critical temperature, that's the superconductor, but above the critical temperature. This purple pinkish phase that you see in this phase diagram here. And that is the object that we try to explain. This is the phase of matter that does not lend itself to the normal explanation in terms of Fermi liquid theory and band theory of metals. This is where the big mystery is. So the immediate question is then, why is this metal strange? What does this theory of metal, what should it explain? And one of the primary hallmarks of it is the so-called linear in temperature resistivity. So the temperature of the resistivity of this metal as a function of the temperature scales linearly as a temperature. Now, you have to take this a little bit in price. It scales linear in temperature all the way down to the lowest temperature that you can measure. Even in ordinary metals at high temperature, there's a linear in T regime, but at low temperatures, normal metals below the bi temperature scaled quadratically as a function of the temperature. So this is the object that we want to explain. And here is experimental data showing beautifully this linear in T resistivity over an enormous range of temperatures up to 600, 700 Kelvin. Now, a second thing the strange metals explain is there's in the AC conductivity, so the conductivity, which is the inverse of the resistivity, but now not for a constant electric field, but for an oscillating electric field, has a very characteristic power law in the mid-infrared around omega, and it scales there beautifully in a temperature independent way as omega to the -2/3. This is also very different from ordinary metals. In ordinary metals, there's a beautiful Drude peak, right, which dominates the transport at low frequencies, the DC limit in particular. And then there's a regime where you don't get a lot of conductivity. And then once you have an electric field which is high enough that you can have interband or interatomic transitions, you again see that the absorption goes up. Another famous example is the Hall angle versus DC conductivity scaling. In an ordinary metal, you can show that the ratio of the Hall conductivity to the ordinary conductivity must scale the same way. It's governed by the same relaxation rate as the DC conductivity in an ordinary metal. So this should go as 1 over the temperature if the linear in T resistivity is true. However, in a strange metal, you see that it scales as 1 over T squared, as if it is an ordinary metal. Well, the two cannot be true at the same time. So this is a puzzle that one needs to explain. There are many other aspects of a strange metal. These are 3 of the most famous ones. And there's one fourth one that I'm going to take in this talk into account. It's a lesser known one, but it's definitely there, is that there is in the AC conductivity, if you go to these higher temperatures, then you see not only this power law scaling, but you also see a mid-IR peak develop. Here you see that at the highest temperatures, 300 Kelvin, you see that there's a small peak in the AC conductivity. In other words, the largest conductivity is no longer at 0 frequency, but it's at some small frequency away from zero. This only happens at really high temperatures. At low temperatures, you have a beautiful Drude peak where the largest conductivity is at zero frequency. So these are aspects that a strange metal should explain. Now, one aspect that you see in it's not just one aspect that is important in understanding this strange metal is it's not just the fact that the temperature is linear that is a problem in these strange metals. Like I said, in ordinary metals, even at high temperatures, there's a linearity regime. What is almost a bigger mystery is the fact that this temperature stays linear in temperature all throughout whatever we can measure. There are no changes in this behavior. And this is very strange. This is not what you expect at all. It's every time you go a phase transition or even a smaller type of transition in the metal, you expect the scaling of the temperature, the scaling of the resistivity with temperature to change, right? And the simplest example is, of course, when you go into the superconducting regime, right? You see that the resistivity changes, it becomes zero. And likewise, if you take slices at different stages, you would expect that every time you go from the pseudo gap phase to the strange metal phase, or whatever other transition there is, you would expect that at those values of the temperature, you would see a change in the resistivity. This does not happen. Somehow or other, this linear in T resistivity is super robust. And it's not just the linearity in T that's robust, let me emphasize, it's the fact that it doesn't change, even though you know that at various temperature regimes, the ordering behavior of the high TC superconductors change. So that is in itself a very big mystery. In fact, in ordinary metals, that's exactly what you see. So that the classic or the simple theory of ordinary metals is that there are three regimes for how this temperature behaves. I already told you that below the Debye temperature, below the phonon decoupling, you expect that the temperature behaves as T squared in the resistivity. Above the Debye temperature, there's a regime where T is, in ordinary metals, the resistivity is linear in the temperature. And then there's a third classic transition in ordinary metals, the so-called Mott-Joffe-Regel limit, above which the resistivity saturates and becomes a constant. The Mott-Joffe-Regel limit is roughly speaking where the scattering rate becomes of order, the scattering length becomes of order of the lattice spacing in the system, and then phonons, which are the main reason for resistivity in ordinary metals, can no longer become stronger because below the lattice spacing there are no extra phonons in the system, and so you saturate. But precisely these type of transitions, and there could be even transitions due to smaller effects rather than this, you don't see in strange metals. And this is in itself a mystery. Now, to describe this, let us briefly review what is the dominant contribution in ordinary metals, or even, as we believe, in strange metals, the dominant contribution to the resistivity. The resistivity in ordinary systems is controlled by momentum relaxation. And this momentum relaxation can either arise from the lattice itself or from impurities. And there's a very simple model, the Drude model, already a century old, which captures this result. If you simply say that the momentum somehow or another relaxes with a certain rate, right? And this is but at the same time, it's accelerated by an electric field N, so the momentum of each single electron. And then you simply say that the current in the system is proportional to the velocity in the system, or in other words, the momentum divided by m. You get a very simple theory of thermoelectric transport, which is Drude theory, which underlies this very simple picture of ordinary metals that we have seen, right? And in a slightly generalized version where you make this non-relativistic version relativistic, the result that you get out of Drude theory has the following form, right? This is the part that's dominated by this momentum relaxation rate. If the momentum relaxation rate, therefore, is very small, this dominates. This is this Drude peak. And then there could be a so-called incoherent, an intrinsic factor to the conductivity as well. These intrinsic factors, or these incoherent factors, are important in the remainder, and you can try to separate them out from the three types of measurements that you can do. You can measure the electric conductivity, you can measure the thermoelectric response, in other words, what happens to the temperature current in the presence of an electric field, or what happens to the electric current in the presence of a temperature gradient. And this is the heat conductivity in the system. And you can sort of extract out this incoherent piece by looking at the heat conductivity in the absence of a charge current, or the charge current in the absence of a heat current. And they are given by these two combinations here. So this separates out these incoherent contributions. Okay. So that is the context in which we're going to discuss. And what I'm going to show you now is in this talk, a simple proof of principle from holography. That in holography, we have found an example where we have a linear DC-resistivity, even though the microscopic dissipation mechanism changes. So in this previous system, we had this momentum relaxation rate. And this momentum relaxation rate in ordinary metals, right? It's that momentum relaxation rate which changes with the temperature in this system. So even though everything is still controlled by momentum relaxation in the system, it's through this momentum relaxation rate that the various dissipative mechanisms act. And usually when the dissipative mechanism changes, you expect a corresponding change in the resistivity as a function of temperature. Here, however, what I've shown you here is an example computed in holography, and I will explain the details throughout the talk, where even though the microscopic dissipation mechanism changes, the resistivity stays essentially linear in temperature. And here's the example. On the left, you see here the DC resistivity as a function of T. And at very low temperatures, you see a beautiful Drude-like behavior. So this is a Drude-like behavior where I have a linear T resistivity. But the linear DC persists all the way to a point where if I look at the optical conductivity, I have some mid-IR peak. This is definitely no longer simple Drude physics. Okay, there could still be momentum. It could still be that momentum relaxation dominates the resistivity, but it does so in a very, very different way than before. And you can even go through that if we go in a slightly different model, I can have a system where I have a regime where I have a linear resistivity. And here I have I start with a regime where this is this peak here on the left in the optical conductivity is this same peak here. And there's a second peak, which is at much higher frequency. And if you go at the higher temperature, these two peaks collide and are left with one large, big, fat peak at high frequency. Even though throughout this regime, the essential temperature scaling of the resistivity doesn't change. So this is a holographic system, right? Which is based on the so-called Gubser-Rocha black hole. But the key part is that this is a holographic system where we have put the strange holographic strange metal in a background lattice. So the key ingredient in this system is that we've made a lattice which communicates with the strange metals through a modulated chemical potential, which has an average, and then there is a cosine wave in the G direction and a cosine undulation in the Y direction. This is the system where we computed this, and here you see the lattice wavelength and the amplitude in this system. So let me now explain in detail where this signature comes from and how it can be that you have this resistivity that is essentially insensitive to the microscopic dissipation mechanism, which you visibly see changing, but it's the temperature scaling of the resistivity does not. So as before, we do this in a holographic metal. We model the strange metal by some electrically charged black hole in an effective ADS gravity. And we use the ADS CFT correspondence to compute the response functions through the bulk boundary correspondence in this system. And as almost all of you know, we're doing this system at an average finite density. So we have an ADS charged black hole. And the conceit, of course, is that this allows us to get to an holographic strange metal state, which is essentially the near horizon gravitational ADS2 physics of charged black holes. These are what strange metals are. There's some generalization of these models, as we all know, to Lifshitz type models with emergent hyperscaling violation. However, the model that we will be considering is we will choose this very specific model with, in this language, the hyperscaling parameter equal to -z, and we take z to infinity. This is the near horizon limit conformal to ADS2, or in a more colloquial terms, the Gubser-Rocha black hole, because this is locally quantum critical with a sort of by scaling analysis already a linear in T resistivity. And the new ingredient that we brought to bear on this is we have introduced a lattice, an ionic lattice in the system, where we have the chemical potential not as a constant throughout, but it undulates. It has a modulated behavior in both the x and the y direction with an amplitude A and a lattice wave vector G. And then we compute the background solution of this, the ground state of this system by, or the ground state, the finite temperature state of this system through numerical general relativity. So these are solutions that are black hole solutions that have, because they're still at finite temperature, they have a spatially varying horizon, and you have to really solve a large set of, in this particular case, three-dimensional partial differential equations to construct these solutions. So you do that, you let your computer compute for 2 years, and then what you get out is you can read off through the ADS CFT the response functions. And if you look at the DC response, sort of what we discussed earlier, the electrical conductivity, the thermoelectric conductivity, and the heat conductivity, you indeed see that in its Gubser-Rocha black hole, by design, a little bit, this is an almost linear NT resistivity at large amplitude. And the same way for the heat conductivity. For comparison, I give here the Rice to Nordstrom solution, which scales rather differently. And this is computed at a relatively small lattice vector compared to the chemical potential. The lattice wave vector is about a tenth. Now, you see this almost linear in T conductivity, and therefore an almost in T linear resistivity. But the main insight or the main message that I want to tell you today is that even though this DC resistivity is almost linear in temperature, if you look more carefully, in particular if you look at the optical response, you see that the dissipative mechanism by which this the energy is dissipated in the system, the energy is lost, is very different throughout this regime where it stays linear. It starts at very low temperatures with an ordinary Drude behavior, but then it transitions to a regime where I have a mid-IR peak, and you can definitely not call this an ordinary Drude response anymore. And you can even go worse. There is sort of an extra sort of colliding peak regime as well, where the mid-IR peak collides with, which we'll show is a sound peak in the system. Now, strictly speaking, all this linear in T resistivity, you should think as a continuum. The only reason why I'm presenting it to you in two pieces is because for numerical reasons, we cannot in one model go all the way from this hydrodynamic Drude-like regime to the mid-IR peak regime, and let's call it the incoherent regime. In reality, we believe that this depends. If I take a fixed A, there is a complete continuous transition from all these three regimes. However, numerically, I can only, for a fixed A, cover two of these regimes. And by increasing the amplitude in the system, I can cover the other two regimes. Even though, in particular, for the large A regime, there are very good physics reasons to believe that if I would be able to compute at lower temperature, I would get back into the hydrodynamic regime where I would still also have a linear in T resistivity. And then I would have an example where I should see a transition between three regimes in one model, even though the linear and T behavior of the resistivity stays the same. So this is a numerical aspect that we unfortunately cannot give you a one coherent picture. But as I go on and explain, I hope you realize that this is really the point of view to take. So let's focus first on the weak lattice. Let's focus first on this top line here. So I have a small a, and I'm going to discuss this transition from what we call the hydrodynamic regime to the mid-IR peak regime, even though, again, throughout this regime, the resistivity stays essentially linear with the temperature. And one way we can do that is we can very carefully look at the poles in the Green's function, the current Green's function, that determine the optical response in the system. And what you see then is the following. You see that if you're at very, very low temperatures, there's not one pole that explains this true peak. There secretly are two poles in this system, right? And what can happen is that as you increase the temperature, that these two poles collide, and then once they collide, there is no longer a constraint that this single pole has to be on the imaginary axis. They can move off the axis. They can start to propagate. And that's exactly what happens. And that is what explains this emergence of this mid-IR peak. So the mystery is that there is all of a sudden, in this lattice model, I have a second pole. Now, where does this come from? If you took a let's try to analyze this in the very simplest way. We have a very weak lattice. We have a very low temperature. We have a very small lattice vector. So you would naively expect that sort of hydrodynamics still works. So let's try a hydrodynamic analysis where we try to explain where these various points come from. And this is also a big lesson from holography, that transport in these systems is essentially always governed by hydrodynamics, right? So we look at hydrodynamics in a relativistic language as before, and we're studying this Gubser-Rocha black hole, which has a near ADS2 horizon, or even it inherited from the UV system. It has a conformal scaling, so the bulk viscosity is 0, and the equation of state is just that the pressure is the energy density divided by the number of dimensions. And then the way you get this normal Drude pole is you look at the fluctuation analysis in this system, where in the longitudinal sector, that's the one that contributes to the DC longitudinal resistivity, there are three modes that couple. There's the energy density, the charge density, and the longitudinal momentum density. And when you do an analysis of this, you find that there are three poles in this system. There's two longitudinal ordinary sound modes that are propagating and are far off. They have a strong real component. And there's one diffusive pole in the system. This is sort of the charge diffusion pole in the system. And that's the one that is ordinarily there. Now, the point is that if I look now in the presence of a lattice, we have to actually redo this fluctuation analysis more carefully. Because if you take any mode in the presence of a lattice, right, what we've learned in our first year of solid state physics is that you should not expand your waves in terms of ordinary Fourier modes, but you should include the periodicity that is inherent in the lessons in the fluctuation analysis. Instead of expanding in ordinary Fourier modes, you should expand in Bloch waves in the system, right? You should expand in the following system. And then a very simple example, if I take a very simple operator, which just is a diffusive operator in the presence of some lattice potential, you can show that in a perturbative expansion that the eigenmodes of the system have the following solution, where these two objects that see they have a pole at half the lattice vector. Those are the Umklapp copies at the edges of the Brillouin zone. This is where you have naively you have level crossing due to the fact that you copy your system, but now because of small interactions, those level crossings become level repulsion, and that's the Umklapp in the system. And the point one point of of my seminar today is that this same analysis you should and you can apply to hydrodynamics. So if you do this, you get it becomes rather complicated, because if I just look at the longitudinal sector, where I had three modes, if I do first order in the perturbation strength alpha, I now don't get three modes. I get one, the zeroth order zone has three modes, but then each of the neighboring Brillouin zones gives another three modes. So if I only limit to the first order Brillouin zones, I already have 9 modes that I have to analyze that are cross-coupled. Fortunately, there is a parity-odd, parity-evening decoupling, where these 9 modes decouple in a set of 4 and a set of 5, and the longitudinal conductivity sits in this set of 4. And if I now do a hydrodynamic analysis of this system, I find 4 modes that are at the following systems. There is, this is the mode analysis at k is 0. But at k is 0, because I now have this Umklapp factor, I can still have modes that reside precisely at the lattice momentum. And you see here that 2 of these modes are the ordinary sound modes, but they're now evaluated not at k at an arbitrary k, but precisely at the lattice momentum g. So these are Umklapped copies of these 2 sound modes. Then there's the ordinary diffusion pole that was here, but there's also an Umklapped copy of the charge diffusion mode that I had earlier. And these are the 4 modes that survive in the system. And the 2 modes that I was talking about earlier are just essentially these 2 modes where I zoomed in and I dropped the 2 sound modes of the system. So this is where this extra mode comes from that I saw in this earlier picture. Let me see. This is where this extra mode comes from right here. This is this Umklapped charge diffusion mode. Okay, so of course, studying hydrodynamics, or particularly transport in strongly coupled systems in the presence of a lattice has been done before. You can do this in a memory matrix type method. In the memory matrix, you indeed find that the dominant contribution, that is this pole, has the same values as the memory matrix component. But what the hydrodynamics analysis gives you on top of the memory matrix is these other 3 modes and their contribution. And here's an example. This is now the sound mode, where you see this level repulsion in the hydrodynamic modes at the edge of the Brillouin zone, precisely at half lattice vector. You can test this rather precisely because you now have, notice that thanks to the hydrodynamics, you have a very precise prescription of the location of this pole in terms of thermodynamic quantities and transport coefficients, as well as the lattice vector. And so you can very precisely predict where this pole should be simply based on the homogeneous system. And then you put it in the small lattice, and then you can see where it is. And here's this comparison. This is the pole that we see in the system, and this is the prediction from this Umklapp hydrodynamics. And you see that this matches beautifully. So this is really the story, what is going on. This is actually what we see reproduced from these undulating charged black holes, numerically computed over a time span of almost a year or more. And now we can understand actually what happened in this weak lattice example that I gave you. Here again, I have this very robust linear DC-resistivity, where I start with this Drude pole, which is actually not a single pole. It's dominated by 2 parts. This is the ordinary Drude pole, which has this sum of 2 relaxation rates that you can also get from the memory matrix. And this lower pole is the Umklapped charge diffusion pole, that is roughly speaking at the value of the charge diffusion constant times the lattice momentum squared. But they're both on the imaginary axis. So in the real part of the conductivity, it looks like you have a very beautiful single Drude-like peak that dominates the low frequency and specifically the DC transport in the system. But as you increase the temperature, these 2 poles can now collide, right? And then they can move off the real axis. And that is the mechanism by which happens. So the Drude pole collides with the charge diffusion pole. They can become propagating. And now you can have a mid-IR peak, right? All of a sudden off the real, off the zero frequency axis. In fact, the similar sort of dynamics of 2 coupled diffusive modes was already illustrated in a somewhat different context by Delacroix, Gubser-Rocha, Hartnell, and Carlson, who looked at decaying charge density waves. And they wrote down this effective formula. If you actually take this Umklapp hydrodynamics that we have, and you focus only on these 2 poles, right? You forget about the Umklapp sound poles, you can rewrite this in exactly the same way. These are these 2 coupled damped oscillators that contribute to the conductivity. What is different compared to the decaying charge density waves in the system is that now the temperature dependence in this Umklapp hydrodynamics is different. The temperature dependence of these effective coefficients, capital gamma, capital omega, and the interaction strength, omega naught, has a different dependence on temperature than in the modulated wave, and we can compute it here. And then you see that in this particular case, what happens is that the poles collide as temperature is increased. Right? And this is again a slightly more detailed version. It's precisely when these two objects, when this gamma minus capital omega becomes larger than 2 omega, that's the point, that's the collision point where these two poles collide. Here you see in more detail a sequence of this collision, and you see how the Drude-like peak slowly transforms in this mid-IR type peak. Now, in a certain way, this is a very unique signal of this collectivization at scales smaller than the lattice spacing. Remember, all of this was computed with a lattice vector g less than mu. I will comment in a second why this is important. But this is a really beautiful story of hydrodynamics, and at this moment I am unaware of any other scenario that can give rise to this mid-IR peak as the temperature is increased in this system. Note that this is very different from goldstone pinning, where precisely you get that this peak moves off zero frequency as you lower the temperature in the system. And that's precisely what I mentioned before. It's precisely this funny mid-IR peak that arises as the temperature is increased, which is seen in real experiment, and Umklapp hydrodynamics may be the explanation of this. In a certain way, you might say this is a first signal that you have hydrodynamic transport in strange metals. That may be pushing it a bit far, but it's certainly a case that you can make. Now, remember this larger context of the story that I wanted to explain. What I wanted to explain is that I have this very robust linear in T resistivity, essentially linear in T resistivity, that as I increase the temperature, I have a real change in the dissipative mechanisms in this behavior. And this is precisely what happens, is that in this particular case, it's the Drude-like pole, or maybe with a small contribution of this guy that controls this behavior. But once I have the two poles collide, it's a much more complicated system where the objects dissipate through. How come the DC resistivity nevertheless stays linear throughout this system? Is there any reason? Because as you see, there are all these contributions in the system, and they have a very different dependence on the average chemical potential, on the charge diffusion constant. This W bar is epsilon plus pli. This depends on the charge transport coefficient sigma q. This only depends, this depends directly on the lattice momentum g squared. They all depend very differently on the temperature. Now, the underlying reason is that you still get a linear in T resistivity, is that when you look at the temperature dependence of each of these combined systems, and those temperature dependence are actually determined by the fact that you flow to this quantum critical IR, this near ADS2 physics, or this Z infinity fixed point. They fix a lot of these scaling properties. You know, the entropy density is not a free parameter. It must scale as T to the D minus theta over Z in these systems. And in these two systems, if you take a generic one of these Lifshitz hyperscaling violating fixed points, they scale like this. So they look the same, but even in a Reissner-Nordström system, this term is absent. So in a Reissner-Nordström system, you would find that these two objects scale differently, but in Gubser-Rocha, they happen to scale the same way. And it's this underlying quantum critical point that is really what protects the fact that this resistivity stays linear throughout in temperature. It's not actually the sort of based on the hydrodynamics and the Umklapp hydrodynamics alone, you would again be reinforced in your prejudice that every time you have a transition in the main dissipative mechanism, the resistivity should change in temperature. The beautiful aspect what happens here is that precisely because at a deeper level, all these thermodynamic quantities are controlled by the Gubser-Rocha fixed point, That is what guarantees you that the resistivity stays linear throughout. Now, I mentioned one thing, that we could apply hydrodynamics in this system because the lattice momentum was small. And this is something that I would want to emphasize. Again, remember, we are computing these black holes with an undulating horizon. And it is really important for this undulating horizon, or this modulated horizon, or the fact that the lattice persists all the way down to the lowest temperatures, that your lattice vector is small in units of the hydrodynamic cutoff scale. And that's a very simple reason that we all know that if I take quantum field theory, in a quantum field theory, the lattice is a UV effect that just normalizes away very, very rapidly. And if you take a very large lattice vector, G is very large in terms of sort of the hydrodynamic scale, that's exactly what happens. Here's an example of the profile in the radial direction of this such a black hole, where I have taken a lattice vector which is 4 times the average chemical potential. And you see immediately it renormalizes very rapidly away, and essentially at low temperatures or close to the horizon, this is just a completely homogeneous system. This is the naive expectation you have based on sort of the UV insensitivity of effective quantum field theory in the infrared. What happens at these lower lattice vectors is that essentially the system thermalizes or classicalizes or hydrodynamizes at scales where you still have a very large lattice vector left. And then sort of the quantum renormalization, the quantum screening ends. And so it stays imprinted for a very, very long time down to the lowest temperatures. Actually, you can prove in the system that nevertheless, at the lowest possible temperatures, this will still become a homogeneous system. It's just that onset is delayed for a very, very long time. So it's important for this effect that the lattice vector is small in units of the chemical potential. And in fact, you can verify this. Here is a same example of, again, the optical conductivity in this system. Now, not even for a super large lattice vector, just G is 1 times mu. And even at the large temperatures, yeah, here's this sort of this sound, Umklapp sound mode. But nevertheless, for the full regime, it's essentially this Drude-like physics, which is dominated by a Drude-like peak. It doesn't mean that these other poles, the Umklapp poles, aren't there. They're just so weak and there's no collision going on and none of this interesting dynamics that you see. This is just very ordinary Drude-like physics. And in fact, this is precisely the sort of the Hartnell-Hoffman type story where you can beautifully explain the scaling of the DC resistivity in terms of the microscopic parameters of this holographic model. So it's important for this scenario that I've described, with this Umklapp hydrodynamics where I have a mid-IR peak, that the lattice vector of the lattice is smaller than the chemical potential scale where hydrodynamics sets in. So I've now explained this transition between this hydrodynamic regime and this mid-IR peak regime. You can understand this from sort of Umklapp hydrodynamics, where you have this extra Umklapp charge diffusion peak. There's a specific temperature at which this Umklapp charge diffusion peak collides with the ordinary Drude peak. The 2 poles can move off, and that gives you a mid-IR peak regime. But you can also try to study the system at slightly larger lattice potentials, the potential strength, to see what happens further. And even though Umklapp hydrodynamics itself as an analysis starts to lose its validity, you can nevertheless beautifully in holography study the pole structure of this system. And here you see the poles in the regime where we started earlier. This is this 2 peaks that have collided and moved off. And now I've zoomed out. And you also see the 2 Umklapp sound peaks. These are precisely these 4 peaks that I gave you in the analysis of Umklapp hydrodynamics. So even though I'm here no longer at weak lattice potential strength, in a formal sense, Umklapp hydrodynamics is no longer valid. You still very clearly see the 4 peaks that you would also derive from an Umklapp hydrodynamics analysis, which would be perturbative in A. And if you look at the optical conductivity, you see indeed beautifully both these peaks. Here, this is this mid-IR peak, the one that we made such a deal about, the one that you also see in experimental strange metals. And here is this other peak. This is the Umklapp sound mode in the system. And you can now change, again, study the system as you increase the temperature. And as you increase the temperature, we've just seen that these poles starts moving. It's now no longer completely, you now no longer can completely explain the movement in terms of thermodynamics, because Umklapp hydrodynamics doesn't work, but you can simply trace what happens as you increase the temperature. And what you see is that these poles, the two poles that of the mid-IR part, they start moving off further and further away until they basically, well, they don't really collide with the sound peak, but they get shielded from the real axis by the sound peak. And in terms of the optical conductivity, it does look like this peak sort of gets eaten by the sound mode. And you have a very amorphous, bad metal-like signature in the optical conductivity. But even so, throughout the system, if you look at the DC resistivity, so the value of the conductivity at omega is 0, you see that this essentially stays linear for a large part of this regime. And again, this is completely understandable in terms of the scaling behavior of the underlying Gubser-Rocha quantum critical IR. And this also then is the reason why we can with confidence say that if we could numerically track this down to lower and lower temperatures, we fully believe that this linear NT regime would continue out through. And actually these points that seem to deviate from linearity, we have reason to believe that they're not as reliably numerically. This is where numerics started to have serious issues. So we actually believe that you should have a full linear regime here all the way up to here, where here you have a very Drude-like behavior. Here you transition to the mid-IR peak behavior. And here you have this bad metallic sound mode dominated optical conductivity. Even though throughout, again, the DC resistivity stays essentially linear in the temperature. So this is the explanation for basically the transport in these holographic strange metals at small and even qualitatively at intermediate strength lattices, where A is less than, or as we saw, even A is order 1, we can still understand a lot of the pole dynamics in terms of this intuitive picture of what happens due to Umklapp hydrodynamics. Now, we worked very hard to compute these holographic strange metals through these modulated, spatially dependent black hole solutions. And we can do more. With the code is not limited. The code doesn't care whether A is 0 or 1. It can do A is 2, A is 3, A is 4, A is 8 with relative ease. So we can simply now ask the question as an explorative one, what happens at large lattice strength? What happens to the thermoelectric transport in such a holographic strange metal if I could make the lattice very, very, very strong? Well, this is what happens. Actually, this is the first thing. But what you see is actually that the resistivity becomes, if at all possible, ever more linear in this system, right? This is the answer for the conductivity. But there's one thing that you should notice is that there is a large part now. This is the sigma Q is 0 part. This is the conductivity in the absence of a heat current. And here you see the ratio of the conductivity as a function of the heat current compared to the ordinary conductivity. And what you see, what happens is that its contribution as A increases becomes stronger and stronger and stronger. And this is actually precisely what is expected, because based on this Drude model, remember that there was this Drude part which was proportional to the inverse momentum relaxation rate plus this incoherent term. And as the momentum as you increase the lattice potential A, of course, the momentum relaxation rate goes up, right? And therefore its contribution should go down. And so the contributions to the conductivities should start to become dominated by this incoherent part. And that's precisely what you see in these systems. Here, there's a large contribution in these systems from the diffusive sector. Here you see it explained in formulas. There's this inverse momentum relaxation rate part, but as A increases, this term gamma becomes, the rate goes down. So this becomes larger and larger, and this so the rate goes up, this becomes larger and larger, and so this term becomes smaller and smaller, and it becomes more and more dominated by this incoherent part. And here you see it in relative terms expressed again, if as a function of 1 over A, so large A is now to the left and small a is to the right, you see this is the full conductivity, and this yellow one is the conductivity at Q equals 0. And you see they start to approach each other. And the same happens for the thermal conductivity kappa without electrical current, that's this green part, and the full thermoelectric conductivity bar kappa, which is this purple part. They start to become equal at very, very small lattice strength of the order of A is 10th. And so this really means that the momentum now relaxes so fast that this collective part, right, this part where the whole fluid sloshes back and forth becomes negligible. And the transport is dominated by this diffusive, this intrinsic diffusive term. There's one thing you should be a little bit careful for, because there's a naive way to always think of the DC transport in terms of this relaxation rate. And if you would do that, even though all these indications are that there is no such collective term, but if you would naively try to extract a relaxation rate in this system for very, very large A, you find something actually rather interesting. You find that the relaxation rate in units of 2 pi t, right, starts to saturate near 1. You have to do it a little bit careful, because as you increase A, there's a transfer in spectral weight, right? So if you compensate for that, that's this compensated form, you really see that this starts to saturate in 1. And gamma in units of 2 pi t equal 1 is a very special value that is very well known in the literature. This is supposed to be the maximal dissipation rate in the system. This is the Planckian dissipation rate, where the dissipation is completely set in terms of natural constants, and there's no intrinsic energy scale left. So if you would not have analyzed the optical conductivity in this system, or not done this more careful disentangling of the diffusive or the collective transport, you would say that this is a classic example of Planckian dissipation in the system. But you have to be more careful, because this is based on an extraction of this relaxation rate through the Drude mechanism. And Drude, of course, assumes that the lattice is weak, and that is not the case here. The more appropriate way to analyze it was emphasized in particular by Hartnell, who wrote a beautiful theory of incoherent metals, is that if you have this very strong translational symmetry breaking, which you have in the presence of a large lattice, you can still do a hydrodynamic analysis, but it's hydrodynamics without a momentum current. You still have a conserved charge, and you still have a conserved energy current, but there's no longer a conserved momentum current in the system. And that means that the analysis becomes a little bit different. You should now only have 2 coupled energy and charge diffusion modes. The longitudinal momentum mode is no longer a Loveland mode. And the way you analyze the system is in terms of the charge conductivity and the charge susceptibility in its relation to 2 independent diffusion constants called D plus and D minus. Now they're coupled, but as was shown by Blake, Davis, and Suchdev, at very low temperatures in these emergent Lifshitz hyperscaling violating states, these 2 modes decouple. And you really have a sort of an independent charge transport sector and an independent heat transport sector. And the same happens, even though this analysis was done not in the presence of a lattice, it was done in the presence of large disorder, or these homogeneous lattices that you can construct in holography. We can verify that exactly the same happens in a real lattice. Here you see the cross-coupling. This is the effective cross-coupling. It's not written here, but this is the effective cross-coupling between the charge flow and the heat flow in these systems as a function of temperature and as a function of the lattice strength A. And as you increase the lattice strength A, you see that this cross-coupling goes down a lot. And also as you decrease the temperature T, you also see that this cross-coupling goes down a lot. So at very large A and very low T, there are essentially 2 independent transport sectors. And here you can see this as well. And then the beautiful part of the story is that the thermal diffusivity in this system, not the charge diffusivity, because that's now completely independent. The thermal diffusivity in the system is precisely set by the scrambling velocity and the Lyapunov exponent that saturates the Maldat-Sena-Schenker-Stanford bound in this system. And this is, of course, what is true Planckian dissipation in this system. In this particular system, you have a Lyapunov rate, which is 2 pi t. That's the real Planckian dissipation rate in the system that shows up in this diffusion constant. And then in this particular case, the VB squared in the system is also temperature dependent. It scales as t squared in the limit of z goes to infinity. What happens in the charge transport sector is still a big question. The charge transport sector does not scale as dt in this system, and we leave that open for open research. That was the same, was found in homogeneous lattices or holographic systems with large disorder. But the thermal diffusivity is completely explained in terms of the scrambling rate and the Lyapunov exponent of the system. So to summarize this story, we've studied the locally quantum critical, the conformal to ADS2 holographic strange metals. They are constructed in this Gubser-Rocha conformal to ADS2 such that they have, on scaling analysis, you expect them to have a T-linear resistivity. And then we have placed this system in an ionic lattice. And what we then showed is that, to also very much to our own surprise, is that this exhibits a very strong robustness in the T-linear resistivity as the dissipative mechanisms in this object change. Thanks to this Umklapp hydrodynamics, right, there are various components or various combinations of thermodynamic quantities that contribute to the dissipation rate. And it could very well be, it could have been that as you change the temperature, one dissipative mechanism takes over from another dissipative mechanism. But that doesn't happen. And the reason that doesn't happen is because actually secretly, due to the underlying criticality of the Gubser-Rocha fixed point, these secretly all scale in the same way. And this way you can explain the exhibit of the emergence of a mid-IR peak in the AC conductivity, which is naively sort of a change of underlying dynamics, even though the linear and T resistivity stays the same. And this mid-IR peak in the AC conductivity is in some ways a true sign of collector transport. And you can make an argument that that is already a first hint that in the experimental strange metals, we actually see this collective transport realized. So with that, I want to thank you very much, and I'm happy to take any questions.
Thank you very much, Koenraad, for your very clear and inspiring talk. Are there any questions? Eric, please go ahead.
Hi, Koenraad.
Hey, Eric.
Video one. Question. So you just explained that the temperature dependence in the conductivity and other transport coefficients, that is set by the underlying fixed point.
That's right.
But what is not so clear to me is how much this story of the poles moving and colliding depends on the underlying fixed point. So in other words, you know, in an experiment, I see the emergence of a mid-infrared peak. What does that tell me about the physics of the underlying fixed point?
So this dynamics does not depend on the underlying fixed point. That just happens. With the following,
even in the case of a Fermi
caveat.
liquid?
What?
Even in the case of a Fermi liquid?
Well, the Fermi liquid is yes, in principle, yes. But the problem is the following: is that whether you can get a collision depends very much on how each of these two poles scales with the temperature, and various other parameters. Okay, and that is set by the how these poles move as a function of the temperature. That is very much set by the quantum critical. So that they will move, and that you have this sort of dynamics. That's universal. But how whether in a temperature range it's feasible or whether you actually see this, right? That depends very much more on the details. And in this particular case, is set by the Gubser-Rocha metal. And of course, in a Fermi liquid, you won't see this at all because in a Fermi liquid, the collectivization scale, right, is much larger than the dynamic scale. And then, as I showed, let me just see if I can quickly you're of course in where that's it. You're of course in this regime where in a Fermi liquid, where the lattice scale is much smaller than the collectivization scale, right? So
yeah, okay.
right. So this only really, or at least based on our holographic insights, but also on simply the applicability of this hydrodynamics picture, right? You must somehow not have that the collectivization, that the hydrodynamics happens at scales of the order of the lattice scale or shorter, right? Whereas that is not what happens in a Fermi liquid. That's why you won't have this in a Fermi liquid.
Well, but it's so for experiments, the challenge will be to determine the various temperature dependencies of two modes if you see them.
Yeah, so that's a very good question, but in this well, let me see where okay, so in this paper by De La Quartas et al., right, where they first sort of made an emphasis on the fact that this peak is seen in many of these strange metals, right? They did a very rough analysis of how the peak location behaves as a function of the temperature, and it seems to be linear in temperature.
Okay, thanks.
There is a question in the chat, actually two questions. One was, does the thus obtained conductivity satisfy any sum rule? I'll let you answer that question first.
Yes, it does. It absolutely does. So actually here, in this small analysis, we use the sum rule to correct for this. Yes, the conductivity satisfies the normal sum rule as before.
I suppose there are several sum rules that one can look for once one has a 2-point function or conductivity. It might be interesting to check for some other sum rules.
Yeah.
So the second question that is in the chat is, are there any predictions regarding the Hall optical conductivity?
The Hall optical conductivity. You mean as in HALL?
Hall, yeah.
Yeah. We're working on that. Okay. Pre-announcement, it will come soon, but no, so far that we have some preliminary data, but in the presence of a magnetic field, and we're working on converting that to a paper version, and I'm happy to report to you soon on this.
Are there any ward identities that would relate?
All the usual ward identities hold, of course.
Yeah, I just don't remember right now if there's anything like correlation functions different from the off-diagonal current correlators that would tell you about the Hall conductivity. So just basically what I'm thinking about is if you can calculate some other correlation functions, and from that, because of the ward identities, derive what the Hall conductivity would be, or just have it as a check. This check the ward identities basically is another way of phrasing this question or thinking of this. So I suppose I was paraphrasing the question that was actually in the chat and that you already answered. Are there more questions?
Martin.
Yeah.
Yeah, so thanks again for this nice talk. I've got two questions. So the first question is about this mid-IR peak. So from my experimental side, so it starts at, say, 200, 300 Kelvin. At least this is what I read off from your diagram. How large can the temperature be? Does it really persist up to 600, 700 Kelvin, or does it also vanish at some point?
That's a good question. I would not know. I would have to look
I can answer that, Koenraad. There are 0 experiments.
Yes, that's what I was.
Okay.
There are very few experiments that go to these high temperatures.
I see. And the second question is a bit provocative one. In some sense, you say we should not take this linear in T resistivity as such a guiding principle for this strange metal phase, because it's just a coincidence. It's fine-tuning, and we were happy to find that in fact, in all these holographic models, it is not a linear in T, but it's only approximately linear in T. So doesn't this mean that it will be even more complicated to come up with a theory of high temperature superconductivity using microscopic degrees of freedom and not like holography?
So I both agree and I both somewhat disagree with it. So let me first go to, so indeed, if in this holographic model, what you see here, you see it is that this is not exactly linear. Whereas, I don't have a good answer to this, right? Because actually, if you look at experiment, it is pretty amazingly linear, much more linear than this thing. So that's not the point. This particular question.
So how many experimental results do we really have which really go up to 600 Kelvin? Is it just one, or is it really more than one that we really know it's
up to 600
universal up to such high temperatures?
But there are thousands up to 200-300 Kelvin, which are really, really remarkably. I mean, from the little I know, and Eric can correct me, this is often actually used as a diagnostic whether you are in the strange metal regime, whether the temperature is linear or not. So that's how robust it is. So there are two things going. There's a technical thing going on, is that we actually really know why there is this slight deviation from linearity is. You can read it in our paper. Is that I don't have an answer to this, but you can actually show that if you do this very, I mentioned that if you're at larger temperatures, you have Hartnell-Hoffman scaling, but actually at larger lattice vectors, but also at small lattice vectors, you still have Hartnell-Hoffman scaling. And when the lattice vectors become very small, there's not one exponent that contributes, but there are multiple exponents that contribute, and they're very close. So actually what you see here is not just a linear in T resistivity, there's a T to the 1 component plus a T to the 1.05 component plus, so we actually really understand the scaling of this in holography super well. And the reason why it's not linear is because you have this mixing of two nearby exponents. Now, of course, that's not what you see in experiments. So I don't have an answer to that. What I do want to say is that simply everybody, when you hear a talk about strange metals, makes a point of the linear and T resistivity. And then what I wanted to make is that it's not just the linearity. The linearity itself is a puzzle, but the puzzle goes deeper than just explaining the linearity. You must also explain why, as you go to various regimes where you expect changes, that linearity stays the same, right? Of course, if you somehow magically pull out the solution, right, maybe it inherently in itself explains why it's so robust. But in most models you compute, right, the first thing you run into is precisely that, oh, I have a beautiful linear T resistivity and I go through a regime change and then I lose my linear T resistivity. But here I have one where this is not the case. That's the message of the story.
Okay, thanks.
Thank you very much for the questions and for the answers. Are there any more questions? If there are no more questions officially, then we will officially end this week's HoloTube by ending the recording and thanking Koenraad again for this very nice and informative talk. As always, we will hang around for a few more minutes after the recording ends. Otherwise, goodbye and see you next week.